researcher at the Institute for Transport Economics in Oslo, and I'm the project manager of the AI Traffic Planner project, which is a collaboration between the University of Bergen, Trondheimsveien, BTI, and Epicron. And I also want to acknowledge Masi Muharat, who had an internship at TUI earlier this year and worked on this model. So as this is an IA-related project, I asked my new chatbot to create a content for my presentation using machine learning to generate an agent-based travel demand representation for the Greater Oslo region. And first he didn't want to give me one, but then I asked him to imagine a presentation, and then he could actually provide me a good table of content. And I will cover most of the suggestions made here, but I have rearranged it a little bit. So for those of you who are not familiar with this type of models, I will give an illustration and some definitions. Then I will give a motivation, and then I will talk about the data and the method. Kan dere høre meg?
Ja, vi hører deg.
Det var noen som hadde på mikrofon.
Ja, jeg mutet.
And I will concentrate on the machine learning part, but I will also talk about the population synthesis. I will also try to validate the method, and this is preliminary. This is the first version of the model, and we will probably refine the model later. And then I will give a presentation of how to apply this demand representation in an agent-based traffic simulation model, and I'm using MATSIM for this. So the purpose of this task is to create a dynamic and agent-based travel demand representation for an average weekday in the Greater Oslo region. And what I mean with dynamic is that it has an explicit representation of day of time. And with agent-based, I mean that I am specifying the travel plans for single persons. So this is a microscopic approach without any aggregation into population segments. And the data representation will be in form of all-day activity plans, which is quite common for activity-based modeling. By the type of activity, the location, and the disabled starting time. And then we derive transport demand from the demand of performing activities. And we predict also the mode of transport in this approach. So here you see an N single agent. Here an ID 877379, and he seems to live in Trondheim, and he drives at 7 o'clock. He drives to his workplace in the east of Oslo, and he is there till around 3:30, and then he goes on a shopping trip close by, and then he drives back to Trondheim. So this is an example of one agent, and then we can execute the activity plan in MATSIM. So this is a short video. Here is this agent is living in Trondheim, and this is only showing how he's driving to the motorway to get to Oslo. And you see in the sometimes the car is turning red, and this indicates reduced speed. And I come back to that how this is simulated. But we can then do this for every agent. And this is how it looks for all the agents. It's actually technically it's a 10% simulation. So we're simulating 10% of all the cars here. And the purpose of this is to see where congestion is building up. And as transport systems are complex systems, this might be very difficult to predict, but these type of models are then a way to simulate this. Traffic flow modeling is only one application of such data. Essentially, you can use this data for all applications where you need a representation of where and when agents are in approximation to each other. So for example, when you want to study the source and exposure of emissions and noise, this is a nice modeling framework because you know where agents are and how they affect each other. And it's also been used to analyze COVID spreading. So the founder of MedSim, Kai Nagel, he when the COVID pandemic came, he switched topics and applied the MedSim model and similar extended the model, of course, but he then applied it to COVID spreading dynamics, and he actually was one of the advisors to Angela Merkel. And because with this type of model and data, you could simulate how the COVID virus is spreading from one agent to another agent. And Kai Nagel, he has a background in computational physics, and he applied these type of models to transport back in 1992 from this paper, a cellular automaton model for freeway traffic. So what you do in this type of models is that you're computing second for second what is happening, and you have single cars here. So this car, which is indicated by the number 4, it moves forward 4 units of space, maybe 4 meters per second, and then you in a way compute second for second what will happen. And when you then have a car that is stopping, for example, and congestion is building up, you see how individual behavior gives emergent phenomena on a more system level. And such behavior is very difficult or impossible to model with static models like the RTM model system that we have in Norway. So I guess most of you are familiar with transport planning and models. We can divide it in 3 groups: operational planning and models, tactical planning, and strategic planning. For example, building a new motorway would be a strategic planning topic. Building a new lane on an existing motorway might be a little bit more tactical. They change the rotor structure, and especially when you have time-dependent toll structure where you need dynamic effects, this would be a more tactical planning topic. And very detailed traffic flow modeling is done in operational models. So in Norway, we use the regional and national transport models for strategic planning, and the Trondheimsveien has also access to AIMSyn for more operational planning. But there has been a lack of tactical planning models, at least as I perceived it. And for example, we didn't have any model who could predict the crowding in trains. And that led to the development of the Trondheimsveien model by the Railway Authority, which is a tactical planning model. And the MedSim would also be a tactical planning model, mostly applied for road traffic. It's not that detailed as these microsimulation models in AIMSyn, because it's using a mesoscopic modeling of traffic flow, but it's quite detailed. And in comparison to the classical simulation models, it also includes demand effects. And when it comes to challenges in the use of transport models in Norway, all of those models, they require expert knowledge to run, and most of the models do not have a very good result visualization, and they take a long time to run into equilibrium. So our AI traffic planner project aims towards more fast and user-friendly transport models. And the core idea is to build a meta model based on AI techniques for fast traffic predictions. And the idea is to use MetSim as a source of producing training data. So these are the partners in the project. Quite diverse team, very complementary backgrounds. Here are some of the persons involved in the project, and yeah, as you see, they're coming from different disciplines. So a simplified data flow of the overall project is that we are departing from real-world data, population data, commuting data, zonal data, and travel survey data. And then we're doing what is called a population synthesis. So we're creating hypothetical agents. And based on deep neural networks, we're generating travel plans for each agent in the population. And these travel plans are feed into the MetSim simulation model, where the plans are physically simulated in the network and where agents have the opportunity to replan, to adjust the plans. And for example, if you want to simulate a change in a network, like increase in travel speed, you could then model the adjustments of the agents to that policy. And this is what we have done so far in the project. And from next year, we plan to build a graph neural network on the training data produced by MetSim. And this will be done by a PhD student, Ruter. And after that, we plan to implement a tool where we can specify scenarios and then can use the graph neural network to give us fast traffic prediction. So you don't need to wait a few hours or a few days to get the results. You can get it probably in a matter of seconds. This is at least the ambition of the overall project. So population synthesis is about generating a population of artificial yet realistic agents that mimic the real population's joint distribution of characteristics. And the generation of activity plans is then to predict the type of trips that the agents in the populations are likely to do. And as I said, we're predicting all-day activity plans for a regular weekday. And the machine learning part I will talk about later is only on the generation of activity plans, not on the population synthesis. But I will also explain the population synthesis because it's an important part of the project. So for training data, we are using a travel survey called Ruter-MIS, which is owned by the public transport provider in the Oslo region, Ruter. And we included data from 3 years, from April 2017 till March 2020. I think in the original data set, we had around 92,000 trips reported. And here you see how the data looks in SPSS. You have one line per trip. And for the first respondents, you see that you have 3 trips. This is a female person between 50 and 66 years. And she reported 3 trips. And this data set can be used to generate activity plans. And this is how an activity plan looks in MetSim. So you have an agent ID and characteristics, and then you have trip characteristics or characteristics for the different activities, and then a leg node which is used to get from one activity to another activity. So these are the background variables which we could load in. And this is the zone of the first activity, and then we can just sample coordinates for that activity. This is the this is the end zone of the first trip, which is the location of the second activity. And we have also respondents report also when they depart for the first trip, which is the end time of the first activity. And it's reported in full hours in Ruter-MIS, but we sample that into seconds and minutes. And the trip purpose is used to define the type of activity of the second activity. And the transport mode reported is used to specify the leg mode in medicine. But we do not do a direct translation of the data set because this would violate GDPR regulations. So we want to have synthetic agents and hypothetical travel plans instead of real observations. And we want a full set of agents. This is over 1 million agents in the case of the Greater Oslo area. So it was not possible, even if we wanted to use only real observations. And also we want to have a more representative set of agents. So we depart from register-based population and commuting data. And we know there are some sample selection bias in travel survey data, and this can be mitigated by our approach. And it's a complete data. We have the full number of agents living in each geographical area, which is called BSU. It's cont in Norwegian. And here you see a map showing the size of a typical cont in the Oslo city center. Here you see in color codes the population density in the Oslo city. And for the whole area of the RTM 23 plus area, we have 2,873 BSU. So this is the whole area. Here you see in color codes car access, which is very good overall, but limited in the Oslo city center. And another advantage of using the official population files is that we have also official forecasts by Statistics Norway, which we can then use to generate future populations. And this is using this official forecast by Statistics Norway is consistent with the RTM model system. So what we did is we generated these agents based on population data, and then we also generated work BSU based on commuting data. This was also, we have the conditional probabilities of each work BSU given the home BSU, and then we just sample from that. From the population data, we have 12, or we segment in 12 initial agent types by gender and age group. And then we split that further up into 144 agent types. The other characteristics are a dummy for occupation status, car access and car type. This is no car type, no car access, access to a normal car, fossil car, and access to an e-car, electric car. And then we have also a dummy if a person at all travels on a given day. And these conditional probabilities are partly based on zonal data from the RTM transport model system and partly based on Ruter-MIS. And now I compare the generated travel population with Ruter-MIS. This is all before we doing any machine learning. It's just the population synthesis. And remember that we are generating the population for an area that is larger than the area of the Ruter-MIS. In particular, we have included Drammen and Moss. So this impacts somehow the comparison. Here we see employment status by age. The upper figure is the generated one, and the lower one is the one from Ruter-MIS. And here I think you see some sample selection bias in Ruter-MIS because it's more difficult to get unemployed people to answer these type of questionnaires. So we see a lower share of unemployed people in Ruter-MIS than it should be in the population. Here you see car access by home region, and here you see the difference because in the generated sample we included Drammen, therefore we have much more observations in the out west region. And the pattern you see here is, of course, that car access is more limited in the Oslo city center. And this one gives you the work distance, which is also an input in the later machine learning model. And I'm a little bit unsure about these color codings because they have different bin sizes here, but I think in overall we have quite similar work distance distribution than in Ruter-MIS. So right now I have explained how we use population data and additional data to generate a set of agents of different types. And the next step is then to predict individual travel plans given the travel survey data. And this is done here by machine learning techniques. And in comparison, you can look at the RTM model system, where you have actually quite similar input data. You have also the same population files. You have the zonal data. And you have travel survey data. It's not Ruter-MIS, it's the national travel survey data, but it's quite similar data actually. And in the RTM model system, you have aggregated population segments and OD matrices, while in our approach we have individual and dynamic data. And the individual travel plans are then weighed into METSIM, where the level of service and the adjustment to the level of service is coming in METSIM internally. And in the RTM model system, you assign the OD matrices on the network and simulate route choice, and then calculate delays, and then this produces you level of service data, which is then also used to predict the OD matrices. So it's a little bit different approach, but it's both approaches are based on population data and travel survey data. So why are we using machine learning to predict travel plans? Well, it's in the spirit of the overall project, and there's also an increasing interest in doing this type of analysis. Here is a state-of-the-art model by Duba-Mathur et al. From this year. I didn't saw this paper before I started with the model. Otherwise, we might have adapted the approach taken here, but we using a somewhat more straightforward approach. In this paper, they have this generative adversarial networks, which are quite nice and would be nice to try also on our data. But we used basically the main motivation to use the machine learning approach was to get a more flexible modeling approach compared to the typical way of doing these type of agent-based modeling, which is based on logit models. So it's here's a comparison. I don't want to go in all the details, but the model input and model output are actually the same. You have agent characteristics as input, and you model the output of the models are probabilities of trips, of trip characteristics, right? And there's somewhat a different interpretation in the deep neural network. It's in a way that the neural networks believe in its predictions, while in logit models, its interpretation is based on choice probabilities from a researcher's perspective. And it's in a way in the optimization, which is both are based on gradient descent, but in nested logit models, you're maximizing a likelihood function given the assumption of the error term. While in deep neural networks, you do not normally assume a distribution over the errors. You're just trying to find the best weights and biases in your neural network, such that you get the best predictive capabilities. And the internal model in deep neural network is a lot of internal functions, weights and biases, so-called activation functions, and the number of parameters is very large compared to the nested logit models, where you have utility functions and then a predefined structure and interpretable parameters, and typically you have much less number of parameters in the logic model. Yeah, and also the data is how you treat the data is a little bit different in machine learning. You split into training data and validation data, and then you run through the training data a lot of times. That's what we call epochs, and this is not allowed in classical statistical models because it would you would underestimate the standard errors of your parameters. Yeah, so this is just a short overview of all different methods, and there's no. It will depend on the application of what you want to choose, I think. So the network, the deep neural network has different inputs: agent type, by age group, gender, occupation status, and car access, home region, work distance, and then the index for the trip number. And for the second trip and the third trip and so on, you also input the characteristics of the previous trip in the network. And in the output layer, you then getting choice probabilities for different trip purposes, end region, start time, travel node, and whether or not this trip was the last trip the agent is doing on that day. And this is a more technical description of the model. So all the 5 output layers, they share the same parameters of the internal model. And that's why we will have a correlation between the outputs of these different types. In total, we have close to 34,000 parameters, which of course is quite huge compared to nested logic models, but it's not so much compared to the large language models I showed earlier. They have billions of parameters. Here you see the accuracy on the training data and the validation data. The model is doing best on predicting the end region and worse on predicting the departure time. Or it's not the departure time, but it's the time, the duration of the activity, basically. And it has also the most categories, so it should be the most difficult to predict anyways. But overall, we were quite happy with these accuracies. And we also didn't, here you see the loss functions, and we didn't see any sign of overfitting, which is a good sign. And these figures show a little bit how the choice probability or the probabilities from the neural network are distributed. So in color codes here, you have the actual travel mode from Ruter-MIS, and here on the x-axis you see the assigned probability for car, and on the y-axis you have the calculated probability of taking public transport. And here you're seeing if the real transport mode was car, then the model assigns a high probability of that choice of being car. Otherwise, if the real choice was public transport, you will see that it assigns a low probability for car and a relative high probability for public transport. And the same is here shown for prediction of trip purpose. And here is a similar figure, but here we're looking at the previous travel node, and this is an input, direct input in the neural network. So here the model is even more confident in predicting the right travel mode. So if the previous travel mode was car, he assigns a very high probability of also car in the next trip. Here for work, for purpose, it's a little bit different because you normally have first the home activity and then the work activity. So here you see with the previous purpose was home, you assign a low probability for home again, and a rather high probability for work and for other purposes as well. All right, and then we do not use the probabilities directly. Of course, we have to sample from those because we want to have discrete outcomes from that method, and then we simply sampling from the softmax probabilities of the output layer. I think it has some clear similarities with nested logic models where you also have probabilities, right? And as we're using the same input and because the output layers share the same parameters from the previous layers, we get, as mentioned, correlation between variables in the output layer. And because we have this recursive feedback where we're predicting based on the previous trip, we will also get a correlation between trips, between consecutive trips. I will show that soon. And this is how we write out the travel plans. As I said earlier, we're having this population data, the commuting data, which is input into the model, and then we predict the next trip. And if the prediction for the last trip is no, then we produce a new trip, and then we're generating trips until the last trip prediction is yes, and then we close in a way the prediction for that person, and when we sample and write out the outcome. So again, I will compare the machine learning generated predictions to Ruter-MIS. Here you see the predicted number of trips, and I just divided by gender. The top figure shows the generated ones based on the machine learning predictions, and the lower one shows the actual distribution in Ruter-MIS. And here it seems that the highest number of trips are 14 in our generated sample, while it is 12 in Ruter-MIS. And you see we're getting a very similar pattern. It's not exactly the same, but I think it's close enough for being approved in a way. And here you're seeing mode choice by car access. And of course, if you do not have car access, you can only be car passenger, and then you have a low probability of taking the car. While where you have access to a fossil car or electric car, you have relative high probability of taking the car. This is especially true for electric cars, where you see that the relative share of public transport is lower than for fossil cars. And this is the same pattern as observed in Ruter-MIS. Here you see mode choice by start region. Again, notice that we have more observations in out west because we're including Drammen in our population. And we're seeing a similar pattern. There are some differences. I think also we underpredict the bike share somewhat. It's better seen in the next slides, I think. Yeah, here you see mode choice giving the previous mode choice. And yeah, here you see again that when your previous mode choice was car, you're very likely to take the car also for the next trip, which of course makes a lot of sense because otherwise you have to, otherwise your car is at your destination and you're at home, which is not very good. And here again, I think we see that we underestimating the bike share somewhat. Here you see the predicted trip purpose given the occupation status. Very similar pattern here. And here you're seeing trip purpose giving mode choice. So these are two outputs from the model, which are seemingly very well correlated. And here you see trip purpose giving previous trip purpose, and here you see some weaknesses in the model that it's predicting a lot of home trips. This is this one, which are not existing in Ruter-MIS, or at least we excluded them in Ruter-MIS. And also there are some differences which are not which you wouldn't expect. For example, this work pairs shouldn't be that high. It also seems that when you add work, then you have a lower probability of making a shopping tour or a delivering tour compared to Ruter-MIS. Another thing which didn't, well, it worked quite good, but not perfect, is departure time. Here you see the departure time that is generated, and here's the one in Ruter-MIS, and you see that we have too little trips before 7 and too many trips in the evening. We are actually not quite sure why this happened, so I think we have to look a little bit more deeply into that. And here's an animation of all the activities over a whole day in the Oslo area. You see here's the city center, and you will see that I can start it. You can maybe start it. Here you see now it's 7:30, and most of the working activities are in the Oslo city center. You see also here the industrial area where nobody lives, but some people work. And yeah, you can spot some of the places where you expect working places. And then you just simulate it's not a simulation, it's only a representation of the activity plans for the whole area. It's only here shown 10% of all agents. All right. So maybe some discussion about the method chosen. I think it turned out to be quite a convenient method. It produces reasonable correlation patterns mostly. So we have the right correlation between agent types and trip characteristics, across trip characteristics of the same trip, and between trip characteristics of consecutive trips, and by extension or also over the whole day. Some weaknesses. So if you look into individual generated travel plans, you will see some illogical combinations like work, home, home, and a rather low share that makes something after work. And also this departure time, as mentioned, is not optimal. And it's also such that the method predicts the characteristics of the first trip without the expectation of what to do later, right? So this is unrealistic to some extent, and maybe we could try to predict the whole activity plan simultaneously. I think we want to try that, but I'm not sure if we have enough training data for that. Okay, the last part of the presentation is based on how we implement this population and this agent plans in MetSim. So MetSim is a widely used and open source framework for transport simulation, agent-based transport simulation. And it's quite it's very different approach compared to the RTM model system. It's more applicable for tactical transport modeling, and it assumes a fixed trip frequency and destination choice, but it endogenously models departure time choice. And it's also it puts less constraints on the rationality of the agents. So it's more in the spirit of complexity economics, while RTM is assuming basically neoclassical behavior of the persons. So you have cost minimization into an static equilibrium in RTM, while in MetSim you have more dynamic co-evolutionary process where you get to a stable situation, but do not calculate mathematically defined equilibrium. All right, so MetSim has inputs. This is the network and the travel plans and some behavioral parameters. It then loads the plans onto the network, makes a physical simulation of all the plans. This is what I showed you earlier. And then the agents observe a score they get from performing the plan. So when they get into congestion, they get typically a bad score, and then they have the possibility to replan, to do replanning, and this is what we call a mental simulation. And then you do this 50 times or 100 times, and then you read out the results. Agents utility is such that they, in a way, you can think of it as that they're collecting utility scores for each second over the day. So for performing activities, they get typically a positive score, and for traveling, they get a negative score, and then they get a total score for the executed plan. And then agents in the mental simulation, they can create new plans. They can say that this is the original plan, and it gets a mediocre score. It could create new plans. For example, here you can take a new route, or depart. Here also depart later, or you can change transport modes as indicated here, or change the route. And what you typically see is that this is over the course of 50 iterations, what is happening to mode choice. In the beginning, you just, everybody takes the shortest route, and then there's congestion. And then typically people choose another transport modes to mitigate the congestion. And then the market share for a car goes a little bit down, and then people realize that, oh, okay, maybe it's not so bad to take the car anyways because other people have switched. And then you can get back to the original market share. This needs some calibration to achieve that, but yeah, that's just an illustration how people adjust over the course of the iterations. And here you see how the average score is in the sample. You see also here that the red one is the worst plan in the choice set, and you also generate bad scores, bad plans, but with more and more iterations, you get closer and closer to an optimal plan. And here you see that after iteration 41, maybe we just said that you cannot create new plans, and you just pick the best plan in the choice set. And it seems that we should have simulated a little bit more here to get to the optimum. Yeah, and the main application in our project is to simulate congestion. And here you see some of the congestion that is simulated in the Oslo area. And we also made a comparison to real-world traffic counts, and this is what we got. We did some calibration on the overall level, but we have not calibrated on a link level. So overall, I think we have a quite decent fit against traffic counts. Of course, there's also difficulties with traffic counts, and they might include other observations. And when there's when there's a lot of congestion, then the traffic counts might not be so reliable. But okay, this is what we got. And then we also applied this to a small case study here on the Trondheimsveien in the east of Oslo. Here you see the link flows in the afternoon, I think that is. So you have the Trondheimsveien, which is quite a busy road, and you have a parallel road which is called Østre Akersvei. And what we simulated now is we reduced the speed limit on the Trondheimsveien, and we also reduced in another one. We reduced also from 2 to 1 lane, so a capacity reduction. And this is what we got. So in the base scenario, we have these are the numbers per 50-minute interval. And when we reduced the speed from 70 to 50 kilometers per hour, we got quite a reduction in traffic. And when we additionally reduced the capacity from 2 lanes to 1 lane, we see that in the morning rush in the westbound direction, we also get a big reduction in traffic. Yeah, basically because there was not physical space for more cars after reduced the capacity. Here you see what happened on the eastbound direction, and here you see the afternoon rush where we have a similar pattern. And then we looked also what happened on the parallel road, and here you see there the traffic increased. in the two scenarios, indicating that some agents, they chose then to use Østre Akersvei and did not longer use the Trondheimsveien. This was just a small case study that we did, and we probably should look more into the results, but we had the time for that. So now I will give a summary, and then you will have the possibility to ask some questions if you want. So it is possible to use machine learning in the generation of a dynamic and agent-based travel demand representation. And so I think that we demonstrated, and it's not an end-to-end solution. It's only a part of the whole process. The current version has some weaknesses, but we think it's likely that we will be able to resolve that with a little bit better modeling and maybe more training data. And we also plan some extensions of the models, and have currently a project where we want to include level of service data in the generation as well. And overall, I think it's quite promising approach, and such a data representation has, as I mentioned earlier, many applications, and not only for traffic simulations. And yeah, finally, I asked my chatbot again to summarize the presentation for me. So based on the summary, can you state a witty and encouraging sentence on the future prospects of the project? And what he came up with is, with better models and more training data, the sky's the limit for our dynamic and agent-based travel demand generator. Okay, I leave it at that, and then I open up for questions from you if you have any. Was there any question in the chat, Hanne?
Nei, det var det ikke foreløpig. Det lov å stille spørsmål på norsk?
Det det.
Ja, da det mulighet for det. Vi gir det et par minutter, og så ser vi. Da avslutter jeg recordingen imens.
Ja.